Hey guys, it's Miss Lamb, and coming in on the side
Because I had to start the video with Mr. Lamb, and today we're going to talk about the next installment about probability.
Independent versus dependent. So if you go to our learning target, I can calculate the probability of independent and dependent events. But the key is, you gotta know what independent versus dependent is before you can do any calculation.
Yeah, it's pretty hard to calculate if you don't know the difference between independent and dependent.
And they're so close to each other, but let's talk about it. The independent one, Mr. Lamb, right under here.
Right here.
What can you tell us about independent?
Well, independent, that's two things that are completely separate from one another. We always talk about dice and spinners. So think about it. When I roll that die, does it affect the spinner?
Nope.
Nah, so those are independent of one another. But if I have a card trick with 10 cards,
okay,
and I say, hey, pick a card, and you take it and you keep it, and then I say, okay, now pick another one.
But I still have this card with me?
But she still has that card. That changes the possibilities of what she can pick.
So let's write that up there. Yours, write one, and I will. So with mine, my one event, my first event.
So independent, the first thing doesn't affect the second thing.
So independent, just like the word says, independent of each
Wow,
other.
she wrote that a lot quicker than I did.
I did. First thing doesn't affect the second, and with dependent, the first event does affect it. It changes.
And I love this, right? We're definitely two math teachers because she used affect and I used effect. Ask your English teacher which one of us was right.
I think it's how we used it, but who cares? I'm sorry. English is very
English
important.
teacher, yes, very important.
All right, let's move on and
So let's talk about some examples of things that are independent and things that are dependent.
Get that practice so you understand what we're doing.
You got to know what it is first before you can calculate. So picking a card,
replacing it, putting it back in.
Here's the key words. So if I take a card out and I put it back, I'm not affecting the second pick.
Independent of each other.
Exactly. Dealing a card to myself and then to another friend. So so to myself means I'm keeping that card, which means when I go to the friend, they don't have the same chances
of getting that card.
Getting the card because I kept one.
Yeah.
That's dependent. Because the first thing we did, me keeping a card, affects what you might be able to get on the second try. Okay? Pick two socks consecutively out of the drawer.
So that's one right after the other. That's
right. That means it's not going back in. So let's say there were 10 socks in the drawer. Okay? I took one out. Now there are only 9 socks in the drawer. So you have a 1 in 10 chance the first time, a 1 in 9 chance the second time.
Dependent.
Excellent. Okay, we'll move this out of the way. Spinning 2 spinners. Spinners don't affect each other.
Independent.
And then rolling a die in a spinner, which is my favorite combination of things. Obviously independent.
All right.
So if the numbers don't change, it's independent. If the numbers change, it's dependent. First got to get rid of that.
Moving on to the
next. Move on to the next one. Well, I'm really having a tough time with that.
All right. First, we want to read it and decide if it is independent or dependent. What is the probability of rolling a 6? Could you give me the right? Yep.
There I go again.
So rolling a 6 and spinning green on the spinner. So if I look over here at my sample space, I have a visual of the die. I have a visual actual sample space of the spinner. And yeah, they're independent of each other. So this is the independent event.
That's a big ol' I.
It is a big old I because I wrote it. All right. So 1 out of 6 chance to get the 6. Green has 1, 2, 3. 3 possible green spins out of 4, 5, 6, 7, 8 out of 8. All right.
So let's do a little.
Can we cross cancel that?
We can cross cancel this. That becomes a 1. That becomes a 2, and life is now much easier because that becomes a 1. That becomes a 16. So our answer is a terrible 1 out of 16.
Oh, can we get that as a decimal there?
We can if we have a calculator, which, oh my goodness, I think we have one right here.
Yep, here we go.
Ooh,
1 divided by 16.
Ooh, 6.25%.
Yeah, he might have known that one.
I cheated because I knew the answer.
6.25%. I'm a person that sometimes does my rounding to just a tenth. So I would probably, as a teacher, accept either one of those two. But anyway, there is our fraction, 1 out of 16, or 6.25%.
And remember, it was independent because this had nothing to do with that.
Okay.
Okay?
Let's go erase that.
And let's look at one more example. Now, this is a great example of a dependent. So if you'll put dependent over there, okay. Oh, you can't put anything because, again, I forget.
Can you tell me why it's a great example? I mean, what keyword told you that immediately?
Well, 1 second. Let me do that and then do this. Except I'm going to have trouble.
Erase
I
it.
got it. Yay! Okay, so what makes it dependent? Because it says, what's the probability of picking a king from the set of cards and without replacement? Which means, how many cards did I start with? I started with 5.
This set has 5.
Okay, and what's the chance of getting that king? It would be 1 out of 5.
But now that king is gone.
But the king's gone because I didn't put it back.
So I'm going to kind of try to erase
There
it
you
out
go.
there.
It's gone.
So how many cards
So
do we
now,
have
how many
left?
cards do we have?
4. How many 10s are there?
Oh, just 1.
There you go.
Oh, look, the denominator changed. We had the same problem, but because we took the king out and didn't put it back, we affected the second one.
Now if I multiply that straight across, 1 times 1 is 1, 5 times 4 is 20, 1/20 is?
5%.
I was just going to check on you.
She was trying to trip me up.
I was. 5% even.
Now let me just show you what would have happened if it was independent. If we put the king back, this would have been 1 out of 5 times 1 out of 5 because the king would have been back inside the deck.
So if we had done
It would have then been 1 out of 25. Or how many percent would that be?
4%.
Very good.
So what was the difference in the percentage there if we were asked that? Like what's the difference?
Looks like
in this?
1% to me.
Looks like 1% to me too.
Yeah.
But just to show you, there's the difference.
But that is probably the best I could show you of the difference between dependent and
The
independent.
sample space changed. All right. Do we have one more? I
don't
cannot remember.
think
Oh, yes,
so.
I think we do. So I wanted to show a full deck of cards because, I'm not sure people play cards as much as they used to. But this is a full set of the clubs, the spades, the hearts, and the diamonds. And the question is, what is the probability of picking a king from the deck of cards, replacing it, and then picking an ace?
So the key here to remembering is, and the reason she really wanted to show you this is, we ask you guys a lot of times about decks of cards.
Yeah.
A lot of times you guys ask us, how many cards are in a deck?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are
Times
13
4 is 52.
Times 4 is 52. My brothers used to call it 52 card pickup when they.
Yes.
Did you just raise
I did.
anything? Okay. So there are 52 cards. How many of them are kings, Mr. Lamb?
Well, I see 1, 2, 3, 4. So
Ooh.
4 out of 52
4
or 1 out of 13.
Now, are we replacing it or are we putting it back?
We're putting it back.
So it's independent.
Yes, it is. It's a big ol' lie.
So then we're going to times that by aces. How many aces do we
Well,
have?
there are 4 of them.
Oh my goodness.
And notice that denominator didn't change. Why didn't it change? Because this is independent.
So I'm going to do that. So 1 times 1 is 1. Oops. And 13 times 13 is 169.
Very
Did
good.
you get that calculator? And do
I
that
sure
for
can.
us? Because we do want to try to do both. Just practice. It's not bad. 1 out of 160, not very much.
Not going to be very big.
Ooh.
That's less than 1%. It's 0.59%.
0.59%. Teeny.
That is less than
probability.
1% chance of happening.
Okay. But
So,
that's an
we
example.
just showed you this one more for the cards than for anything else.
Yep.
And plus it does show you. that
Well,
the number does.
and sometimes, can I just offer a minute? Sometimes everyone says, but I'm only going to pick one card.
Yeah,
But there are 4
that's
possible.
right. You have to think about
So
the
you
fact
do
that there
have
are
to-
4.
You really do have to think about that.
So
Okay.
the probability is a thinking man's game.
Yep. Which is why we like it.
Or a woman's.
Or women's. Yeah.
I think we've shown them enough examples.
No, come on, man. All right.
Okay,
Ah. Then the jelly bean candy dish. There are 18 red, 20 green, 12 purple, 15 yellow. You want to add those numbers up?
What is the probability you will select a green jelly bean, eat it, and then pick a purple jelly
Well,
bean?
you
I will figure out your total.
Oh gosh, I went the wrong one. I was trying to get. See, I was trying to get.
It's okay. We got time.
Okay, do it, Mr. Leon.
I am 18.
Probability
20
of
plus 12
green
plus
followed
15.
by purple. But before we do that,
We have 65 total.
No, wait. We ate it. So that makes it dependent.
Makes it dependent.
So we have 65 to begin with. But what I want to show is that I know if I eat it, there's going to be 64.
Again,
So
what's the difference between independent and dependent? The denominator.
that's really why I wanted to show this one.
Yeah, I'm
is
sorry, I
because
shouldn't have tried to rush.
before I did anything else, I wanted to show that I knew that was going to go down by 1.
So we have 20 out of 65.
20 out of 65 times.
And we're looking for purple 12 out of 64.
Now, Mr. Lamb is going to instantly want to reduce, but what I want to do is not waste our time. To be honest with you.
Okay.
Mr. Lamb, 20 times 12. Let's go.
240.
240. Nice big number. 65 times 64.
Oh my God, did I break my calculator?
There's a method to my madness here, and I'll show you.
4,160.
4,160. Now, the reason why I wanted to do this is because if you're looking for a percentage, who cares if this is in lowest terms? 240 divided by 4,160 is, as a percentage,
5.76%.
5.76%. And if you were rounding it, 5.8%. And I guess my point is sometimes we get so obsessed with getting the fraction in lowest terms. But if your ultimate goal is a percentage, who cares?
It doesn't matter.
Use the calculator. That's what it's for. So again, a very small percentage, but very easily solved. Okay?
Okay, so basically the thing to remember, independent to dependent, independent, these denominators don't affect one. I mean, those things don't affect each other's denominator. But in a dependent one, something's going to change.
This goes down by 1. The denominator reduces by 1. Absolutely. All right? So, if you are confused, you might want to watch it again or go on and watch the next video. If you've got it, return to that assignment. Okay? Return to your assignment page, sorry, and start your practice.
Start your practice.
Whoa,
we'll
I'm
see
sorry.
you next time.
I was trying to get him over to go ahead and say goodbye.
But I wanted to say goodbye for a change.
Goodbye.